Hello friends, today we will discuss about the processor architecture subject in which the second unit, the point of discussion is the interrupt vector table and something more points are there. The points of discussions we will cover in this lecture are interrupt vector table, steps in executing the interrupts, sources of interrupts, enabling and disabling the interrupts, priority of the interrupts. The interrupt vector table, it defines where the code of the particular interrupt execution routine is located in a microcontroller memory. The microcontrollers or the microprocessor supports hundreds of the interrupts and execution. Each interrupt execution has the interrupt service routines defined somewhere in a code memory. But the question is how the processor determines where the ISR is located in a code memory for a specific interrupt. The question is simple. Microcontroller makes the use of the interrupt vector table to find the starting address of the ISR, that is a interrupt service routine. The interrupt server vector table consists the address, a functional pointer of the interrupt service routines, that is the ISR, and exception handler functions. The interrupt vector table is a table of the memory addresses of the interrupt executions handler routines. In other words, it defines where the code of a particular interrupt exception routine is located in a microcontroller. There are types of the memories in a microcontroller such as a code memory or a data memory. The interrupt vector table stores at a starting address of the code memory, that is 00F, or because the microcontroller has a 154 total exceptions including the system and a simple exceptions. Therefore, our vector table contains 154 entries. The first two of the stack pointer and the address of a reset handler function. The figure shows a interrupt vector table along with their memory addresses and a memory content. Each memory address contains the address of the exception handler. When an interrupt X is occur, the interrupt request will be sent to the nested vector interrupt controller NVIC. If a NVIC, that is a nested vector interrupt controller, accepts the exception or a interrupt request X, the next step of the NVIC to find the starting address of the interrupt service routine or exception handler. The starting address of the respective ISR or a exception handler is stored inside the interrupts vector table. Then a NVIC uses the exception number X to calculate the address of the exception by looking up the interrupt vector table and use the contents of the memory addresses, which is an address of the respective exception handler, to execute the exception handler. A program counter will be loaded with an address of an exception handler and the microcontroller starts to execute the exception routines. Now, the next point is the steps in execution of the interrupt. When an interrupt gets activated, the microcontroller goes through the following steps. The microcontroller closes the current execution instruction and saves the address of the next instructions on the stack. It also saves the current status of all the interrupt internally, that is not on a stack. It jumps to the memory location of the interrupt vector table that holds the address of the interrupt service routine. The microcontroller gets the address of the ISR from the interrupt vector table and jumps to it it start to execution the interrupt service routine, which is the RETI, return from a interrupt. Upon executing the RETI instruction, the microcontroller returns to the location where it was interrupted. First, it gets the interrupt program counter, that is a PC address from a stack by popping the top byte of the stack into the program counter. Then it starts to execute from that address. So next one is the sources of the interrupt. The microcontroller has 14 interrupt sources. From the diagram below, you can use all the sources of interrupts when XXFI is interrupt flag and XXIE is an interrupt enable. Interrupt flag shows the result of an interrupt, and interrupt enable bit is used to enable or block the interrupt. The interrupts on the left side of the figure given below are a low priority, and on all of them together can be blocked by enabling a bit interrupt, that is a PEIE. So this is the sources of the interrupt, it having the 14 interrupt sources which are shown in this, in which if IF is shown against the interrupt, it is an interrupt flag, and if IE is shown against the interrupt, that is a interrupt enable bits. So interrupt enable bits is used to enable or to block the interrupts, whereas the interrupt flag shows the result of the interrupt and a next point is the enabling and a disabling of the interrupt. The facilities provided in a microcontroller must give a programmer complete control over the event that takes place during the program execution. The arrival of the interrupt request from an internal device causes the processor to suspend the execution of one program and start the execution of another program. Because interrupts can arrive at any time, they may alter the sequence of the events from the evasion by the programmer. Hence, the interrupts of a program execution must be carefully controlled. Let us consider the detail that specific case a single interrupt from one device. When a device activates the interrupt request signal, it keeps this signal activated until it learns that the processor has accepted its request. This means that the interrupt request signal will be activated during the execution of the interrupt service routine, perhaps until an instruction is reached that access the device is questioned. The first possibility is to have the processor hardware ignore the interrupt request line until the execution of a first instruction of the interrupt service routine has been completed. Then by using an interrupt disable interrupts as first instruction in a INTR to name the interrupt request interrupt service routine, the programmer can ensure that no further interrupts will occur until an interrupt enable instruction is executed. Typically, the interrupt enable instruction will be the last instruction in an interrupt service routine before the runtime from the interrupt instruction. The processor must program the execution of a routine return from interrupt instruction in a complete before a further interrupt can occur. The second option, the processor automatically disable the interrupts before starting the execution of the ISR. After saving the content of the PC and a processor status PS on the stack, the processor performs the equivalent of executing an interrupt disable instruction. It is often the case that one bit in a PS, that is a processor status register, called a interrupt enable, indicates whether the interrupts are enabled. In the third option, the processor has a special interrupt request line for which the interrupt handling circuit responsible responds only to the leading edge of the signal. Such a line said to be edge triggered. Next point, we will see a priority of the interrupts means whenever the interrupts are raised, it has the certain priority. Priority interrupt is a system which decides a priority at which various devices which generates the interrupts signal at a same time will be serviced by the microcontroller when two or more devices interrupt the computer or a microcontroller simultaneously. The microcontroller serves the device with a higher priority. First, a decisioning priority is one of the way. In a decisioning system, all the devices are connected in a serial form. The way of deciding the interrupt priority consists of the serial connection of the all devices. The devices with a highest priority is placed at the first position, followed by the lower priority devices and a devices which having lower priority among all these placed at a last in the change. In the decisioning system, all the devices are connected in a serial form. The interrupt line request is common to all devices. If any device has an interrupt signal in low level state, then the interrupt line goes to low level state and enable the interrupt input in a microcontroller. When there is no interrupt, an interrupt line says in a level line, then a microcontroller responds to the interrupt by enabling the interrupt acknowledge line. This signal is received by the device one at its PI input. The acknowledgement signal passes to the next device through the PO output only if a device one is not requesting an interrupt. Following figure shows the block diagram for a daisy chaining in which a number of devices are connected and where interrupt requests and interrupt acknowledgements are given to the controller. It continuously check for our devices one by one and having a highest priority devices connected to the upper line where the lower priority devices are connected to the lower line, and whenever the priority comes for the higher devices, it will give the microcontroller gives the access to that particular device. In this way the daisy chaining works. So thank you for watching the video.